Hello, everyone. Welcome. My name is Jennifer Nyman. I am a senior principal at Geosyn Consultants in Oakland, California, and the coordinator of the SERDP and ESTCP webinar series. I will be facilitating the webinar today. The webinar today focuses on DoD-funded research on structural repair technologies for defense assets. Dr. Jason Patrick and Dr. J. Brian Jordan will share results on how solid-state additive manufacturing and self-healing composites can restore and sustain defense structural assets. Each of these two presentations will be followed by a question and answer session. And depending on time, we may conclude the webinar with a final Q&A session. The next two slides provide instructions on optimizing your webinar experience. If you haven't done so, you can download Zoom at the link shown here and provided to you in your registration email. If you cannot download Zoom, you can still view the slides using a browser like Firefox, IE, or Edge, and by creating a free Zoom account. And if your screen freezes, you can try keying Control with F5 to perform a hard refresh. In case of continued technical difficulties, you can always download a PDF of the slides from the webinar webpage and call into the conference line provided to you in your registration email. Finally, we will also be live streaming the webinar on the SERDP and ESTCP YouTube channel at the link shown here. Today's broadcast is listen only, but we do want you to submit questions. You can submit questions using the Q&A box on the Zoom screen. You don't have to wait until the question and answer period to submit your questions. It would be great if you submitted them in advance of that session. When you submit your question, please add your organizational name at the end of your question. And please don't use the chat box in Zoom for questions. That is reserved for comments related to technical difficulties. With that, I would like to introduce Dr. John Lascala, who is the SERDP and ESTCP Program Manager for Weapons Systems and Platforms. Prior to joining SERDP and ESTCP, John served as the Chief of the Manufacturing Sciences and Technology Branch in the Weapons and Materials Research Directorate of the DevCom Army Research Laboratory. Throughout his career, John worked on bio-based thermosetting resins for adhesives and coatings, and environmentally friendly polymers for composites, coatings, and additive manufacturing applications. John is the recipient of numerous awards for his work on polymers, including the 2013 Presidential Green Chemistry and Engineering Challenge Award for Renewable Thermosets and the 2010 ESTCP Project of the Year. John, please proceed.
Thank you, Jennifer. I'm happy to welcome everyone today to the SERDP and ESTCP webinar. This particular one's focused on two technologies applicable to structural repair of weapons platforms that are also applicable to commercial applications. So I look forward to the presentation today. The next few slides, I'm going to basically give an overview of SERDP and ESTCP. These programs are the DoD's installation innovation programs that develop and demonstrate innovative, scalable technologies that enhance military readiness, improve warfighter capabilities, and strengthen defense infrastructure. The programs prioritize cost-effective solutions that support operational effectiveness and reduce regulatory burdens at military installations. SERDP invests in lab-based research that supports and secures DoD installations, materiel, and platforms. It is managed alongside its partner program, ESTCP, which demonstrates and validates novel technologies in military installations. ESTCP demonstrations collect unbiased cost and performance data to support defense managers and end users with the information they need to implement approved technologies and facilitate DoD adoption at scale. SERDP and ESTCP report to the Deputy Assistant Secretary of Defense for Energy Resilience and Optimization, headquartered at the Pentagon. We work closely with other OSD programs, the services, and defense partners to facilitate the adoption of successful technologies. By fostering cross-program integration, we ensure that promising innovations do not remain isolated research efforts, but transition effectively into operational use. Our projects align with national security priorities and provide the data and capabilities that DoD leadership need to shape guidance and instruction aimed at securing our military installations. Our science and technologies protect built and natural infrastructure, strengthen DoD chemical and material resilience, and ensure the health and safety of our warfighters. Our research portfolios are organized across 6 program areas. The Environmental Restoration Program area focuses on managing PFAS and other emerging chemicals of concern in the environment. The Resource Conservation and Resilience Program area focuses on sustaining the 28 million acres of DoD lands for test and training operations. The Weapons Systems and Platforms Program area that I manage focuses on strengthening DoD's long-term chemical and material resilience, extending the service life of mission-critical weapon systems and platforms while reducing costs and enhancing the safety and efficiency of military operations. The Installation Energy and Water Program area demonstrates and validates technologies that improve access to reliable and resilient sources of energy, providing greater flexibility in the control and delivery of power. The Natural Hazards Adaptation Program area demonstrates technologies to ensure DoD installations can withstand and recover from events such as earthquakes, hurricanes, floods, and wildfires. And finally, the Munitions Response Program area focuses on unexplored ordnance in the underwater environment, including ponds, lakes, rivers, estuaries, and coastal ocean areas. After years of successful investment, this program area is currently transitioning technologies to end users through a series of test sites and live site demonstrations. SERDP ESTCP are a critical funding source and partner for hundreds of federal, university, and industry R&D efforts. We release solicitations throughout the year. Researchers from federal government, private industry, and research institutions can apply to SERDP and ESTCP funding opportunities. With that, I'll also mention we have our BAA, which is out at any time. You can apply online through that, really at any time during the year. If you have a great idea, we're happy to consider it. To receive updates about funding opportunities, program updates, and upcoming webinars, you can sign up for our mailing list at the link on this slide. Our webinar series highlights outstanding project. Our webinar series highlights outstanding project across our research portfolios. You can find additional information from upcoming webinars at the link. All past webinars are archived and can be accessed using that particular link. I'd like to remind you that a copy of the presentation can be downloaded from a webinar page, and we would appreciate if you complete the survey at the end of the webcast that will pop up on your screen. At this point, I'm going to turn it back over to Jennifer to introduce our speaker.
Great. Thank you so much, John. Now my pleasure to introduce our first speaker, Dr. Jason Patrick. He is an associate professor in the Department of Civil, Construction, and Environmental Engineering, with an affiliate appointment in Mechanical and Aerospace Engineering at North Carolina State University, Raleigh. He is an internationally recognized expert in developing bio-inspired polymeric material systems that exhibit multifunctionality for enhanced performance, reliability, and longevity. Jason has served as a principal and co-principal investigator of projects funded by SERDP, the Air Force Office of Scientific Research, and the National Science Foundation. He earned his doctoral degree in structural engineering from the University of Illinois, Urbana-Champaign. Jason, please get us started with your first presentation.
Great. Thank you for the introduction and opportunity to present here today on some work that we've done towards sustained self-healing and structural composites. All right, so brief outline for my talk today. I'm going to go over some motivation and background for the work, talk about the new self-healing strategy that we've developed, our research approach, results and relevance, summarize with some conclusions and highlight benefits to the DoD. And the statement of work for this project was really to develop sustainable field repair technology for damaged composites in advanced Gen 5 aircraft and also future aircraft structures and components. As we know, composites are very versatile materials. They're pervasive in modern engineered structures due to their high specific strength stiffness, corrosion resistance, and geometric constituent kind of functional versatility. And you can see various applications here, including aerospace, military, commercial, naval, automotive, energy applications, and beyond. Now, these hierarchical materials that leverage these properties or inherent properties of the constituents to give mechanical advantage also are inherently susceptible to damage. And I show a schematic here that highlights the various modes of damage at different scales, all the way from chemical debonding up to impact, puncture, and rupture on the high end. And we're really trying to address the issue of interlaminar delamination, or the separation of the reinforcement from the continuous matrix. And so I show a few images at the bottom of this slide. On the bottom left, showing a laminated woven composite, where you can see the nice layered structure. In the middle, you can see this hierarchical arrangement of bundles of fibers or tows and different orientations. And then these interlaminar delamination that I speak of, where you have basically separation of the reinforcement from the matrix, or this adhesive debonding mode. And that's can be a critical factor in the lifetime of structural composites. And so damage is costly and dangerous. Manual repairs are expensive and labor resource intensive. And in the cases where damage cannot be found either through non-destructive testing or remains hidden in a structure, these can lead to kind of catastrophic failure due to the brittle failure modes associated with fiber composites. So there really is a need to find repair technologies for this. Now, if we look towards biology, that can provide some inspiration for self-repair of these type structures. And on the far left, I show a few schematics of biological self-healing and soft skin, and also structural bone, that have inspired researchers and folks to think about novel ways to repair synthetic structures. And if we look at some of the synthetic self-healing strategies in the middle, on the far left, you see capsule-based approaches where these microcapsules are embedded inside polymeric materials that are filled with reactive payloads. Upon fracture, rupture and release those contents and can polymerize and repair cracks. These are, however, limited by single heal cycles and small-scale repair due to the size limitations of those capsules. And so an evolution of that evolved or came into vascular-based systems, much like blood vessels in the human body, where reactive contents could be housed in that vasculature. Those had shown the ability to restore larger damage volumes and multiple cycles, but mixing is a challenge with those systems, and blockages from cross-contamination or polymerization resulting in synthetic scarring. And so another approach is looking at intrinsic self-healing strategies, which rely on inherent dynamic rebonding within the material itself that can restore damage. These can achieve multiple heal cycles and don't require an external agent. And a few examples of the intrinsic healing on the far right, shown in the top, for soft materials, a gel that can be repaired at room temperature simply by putting the two severed halves back into contact. And in structural materials shown on the bottom, a cross-link thermoset material. However, with these structural components, external energy is often required, often in the form of heat. And in that case, we call that repair strategy thermal remending. And so I'm going to highlight today a new thermal remending strategy that we came up with for fiber reinforced polymer composites. And so this new approach that was patented for this technology enables sustained self-healing below the thermoset, or in this case, epoxy matrix glass transition temperature. And we do that via in situ resistive heating. And so on the far left, you'll see a schematic of a 3D printer where we deposit our healing agent, which is a thermoplastic copolymer known as polyethylene comethacrylic acid, or EMAA, that I'll use for short throughout this presentation. And that's deposited directly onto the reinforcement of the layup. We then stack additional layers of reinforcement along with these resistive base heater inner layers, and the entire system is infused with the thermoset epoxy resin that's then cured and solidified. And then, due to some unique physical and chemical bonding mechanisms of the EMAA healing agent and the epoxy, when a fracture does occur, rather than an adhesive or debonding type mode, we get this cohesive fracture between the thermoplastic that, upon application of electrical energy that resistively heats the structure, we can repair and remend those fractured interfaces. And so the functional components here that we add to these composite systems are textile resistive heaters that allows us to achieve that in situ heating. Those consist of a conductive network or percolating network of conductive carbon whiskers that are encapsulated by dielectric insulating glass layers to prevent electrical shorting. And you can see a cross-section of that laminate stack here. The polyethylene comethacrylic acid is taken in pelletized form and processed into filament and 3D printed. And this material is readily available and is adopted from the food packaging industry and an environmentally friendly solution. In terms of preform patterning, we looked at a variety of these serpentine networks at different densities. And so we directly print that healing agent onto the reinforcement. You can see a variety of patterns shown in the scanning electron micrographs in the left. And you can see the relative size scale of these printed domains in blue in correlation to the fiber toes in the composite. I show a cross-section, optical cross-section on the far right, where you can see that EMAA incorporates quite nicely in between these toes of fibers. It actually displaces regions where matrix would occupy. So there's really no weight gain due to the EMAA in this system. And you can see the resistive heater interlayers also incorporated. And below that is a 3D X-ray computed tomography reconstruction where you can see the entire laminate structure fabricated. Now, we wanted to look at the impact of these functional components on structural integrity, which is critical for aerospace and other applications. And so we looked at in-plane tension testing according to ASTM D3039. We used digital image correlation to capture full field strain fields. And you can see a plot of stress versus strain in the middle plot for carbon and glass fiber reinforced composites. Now you'll immediately notice that carbon fiber is stronger and stiffer than glass as expected. And we looked at a variety of different configurations to assess the impact of these functional components on structural performance. And the top right plot, I'm showing a baseline composite value for ultimate strength and normalized values in the bottom of these bar charts. But you can see when we add the addition of this printed interlayer, there's very small impact on structural performance in both glass and carbon fiber. However, we noticed when incorporating the heater alone, while in glass there was minimal impact, in carbon fiber we saw about a 20% drop in structural performance. And that was due to the fact that there are these glass layers in the resistive heaters for electrical insulation, but also drop mechanical properties in these stiffer, stronger carbon fiber systems. However, when we put all components together, we don't see any further reductions due to the EMAA interlayers, signifying to us that the printed functional healing agent doesn't contribute to any detriment in structural properties. However, it was really more related to the resistive heaters, especially in the carbon fiber. And so we worked with an industrial partner to develop a Gen 2.0 heater system that gets away from some of the limitations, again, a percolating conductive network. And we found in that case, in comparison to this Gen 1 on the top plot, but in this bottom right plot, you can see that the heater retains much higher structural properties, only about a 10% drop in performance in this case in the carbon. And so we were very pleased that we could maintain structural performance with some optimization of that material platform. We also needed to conduct thermomechanical characterization to ensure that this material would not experience any detriment during the remaining procedure. The idea was to have in situ repair or in-flight, in-service repair in case an asset suffered damage. And so we looked at dynamic mechanical analysis to determine the glass transition temperature, at which point these structural stiff polymers would turn to a rubbery, more compliant system, and that was around 140 degrees C. And we can see that the elastic or the storage modulus at the TG drops by about 50% in both glass and carbon fiber systems. There is some retention of structural integrity due to the ceramic fibers, but 50% drop is not something we could live with. And so if you go 10 degrees below that glass transition, about 130, you can retain 85 to 90% of your structural integrity. And you can go even lower in temperature and still preserve higher properties. And this healing agent melts around 80 to 90 degrees C. So we're still at temperature ranges much higher than we would need to actually perform the repair. And so for this study, we looked at 130 degrees C. We needed to calculate the amount of power that would require, or the heaters were required to get to that temperature. And so that set the baseline. We did a series of investigations to show at about 12 to 15 watts we could reach those power densities. And that's somewhere around 1/5 of a 60-watt light bulb to achieve that performance and still maintain structural integrity of that system. And so the way we evaluate mechanical properties, we're looking at delamination or mode 1 fracture using this double cantilever beam geometry. We apply a tensile loading on the arms of this DCB and propagate a crack from a pre-crack of 50 millimeters for a 1 millimeter, or excuse me, a 25 millimeter wide sample. So about a 2-inch by 1-inch delamination region that we open up in the sample. You can see the test set up here. We have a series of infrared cameras and also optical cameras to monitor the temperature profile, but also the crack propagation in the sample and apply heat to that. And so a load displacement plot highlights this linear elastic load up until crack propagation, at which point we propagate 50 millimeters and then unload the sample. And we're able to calculate this G1 or the mode 1 strain energy release rate by looking at the area under this load displacement curve divided by that incremental crack width. And then we perform the in situ self-healing, which is 15 minutes of power application. You can see that sample heating up, and then we allow that to cool down via natural convective cooling. And so on the bottom right, you'll see this transient temperature profile. It takes about 5 minutes for the sample to heat up. There's a 10-minute dwell and then a 30-minute cool down. So a sub-hour self-healing cycle. And in comparison to prior healing technologies took on the order of several days, this is a much more rapid approach to repair and can be done in situ. And then to quantify self-healing efficiency or the recovery, we retest the sample, and then we look at the comparison of this healed compared to the virgin curve. And we can take that G1C metric and divide that by the virgin or baseline and multiply by 100%. And that gives us how much recovery we have. And so you can see in this case, the area under these load displacement curves are virtually the same. And so the healing recovery in that case is close to 100%. We, providing some results here, we looked at fracture toughening and the healing response. And so we can see immediately that this virgin fracture resistance, or this first cycle, in comparison to a plain composite at about 500 joules per meter square, is up to 2,000 depending on the aerial coverage or volume percent, which is less than 2% in this case. And we can get about 200 to 400% toughening. So a drastic increase in the fracture resistance. That's due to a number of mechanisms, but notably one shown in the image below is the EMAA fibrillation. This is a tough ductile material, and so propagating a crack through that is more difficult than the inherent matrix, and so that gives rise to that toughening behavior. You can see we've compared for different aerial coverages on the right, and across 20 different repair cycles, we see very steady and reliable repair performance for this system. And again, much higher than we would see for plain glass or carbon composites, which are somewhere around 500 joules per meter squared. And if we look at that healing efficiency metric, which is the ratio of G1C healed to virgin, we can see we can reach healing efficiencies upwards of 100%. And that's 100% on top of the 200 to 400% toughening that we experience. So a very well-controlled system that's reliable and provide that repeatable repair performance. We also looked at the effects of the pattern on crack propagation. And so we had these serpentine networks where we looked at both longitudinal and transverse orientations. And we really didn't see a large difference between the two patterns, except at the lower densities, this 12% aerial coverage, where you can see evidence of this stick-slip behavior, especially in the transverse configuration. And that's simply due to those EMAA traces providing resistant to crack propagation, and in some cases pinning the crack. But as you get to these denser patterns, the healing agent becomes more homogeneous in terms of the crack propagation, and so we don't see a huge difference. I do want to note that, however, in the largest aerial coverage, this 36% in the transverse configuration, we were actually able to shift the failure mode from an interlaminar delamination to a translaminar delamination, which was due to over toughening that interface. And so there's a limit to which we can toughen, at which point we may transition to different failure modes. But we can effectively suppress interlaminar delaminations with this technology, and understanding the limits of that is important to maintain structural integrity overall. And so we also looked at the difference between glass and carbon fiber recovery, especially at this 24% case, or kind of intermediate coverage. And what we noticed was that glass fiber composite showed better recovery than carbon fiber. And we looked at a series of scanning electron micron images of the crack plane. You can see some of the operant mechanisms, the inherent debonding from carbon and glass fibers, that brittle kind of adhesive debonding, versus the more ductile, tearing, cohesive type mode of the EMAA. And interesting, what we see is there's this formation and evolution of a microporous network in the EMAA that's due to some condensation reactions during the epoxy cure, where water pockets are formed, and then during the healing cycles are vaporized and form this pressurize and form this microporous network that helps distribute the EMAA throughout the crack plane and provide additional coverage. Now, interestingly, by heal cycle 20, we saw in carbon cessation of that microporous network versus the still present in the glass fiber composite. And so we continued to cycle these samples up to 100 heal cycles. You can see all 100 traces here. Very, very repeatable performance and much higher recoveries and G1Cs compared to a plain composite. And in comparison to existing self-healing composite technology at the time, this was an order of magnitude beyond cycles had been demonstrated. And you can see how that healing efficiency increases and then slowly and steadily declines, and apparently, or seems to plateau at about 85%. And we looked at the comparison between glass and carbon, and surprisingly, there was almost a constant difference between the evolution of those two recoveries. And if we looked at scanning electron micron images, by about heal cycle 40, we indeed saw cessation of that microporous network evolution, signifying that those interfacial chemical reactions ceased to occur at that point. However, recovery was still possible through polymer chain entanglement of the healing agent itself, leading us to believe that this was a very robust technology and could be cycled even further. And the 100 cycles were achieved with manual intervention. And so we fully automated our experimental setup, where we integrated the thermoelectric mechanical performance and instrumentation and measurements. And in that case, we were able to see another order of magnitude increase in healing cyclability, reaching 1,000 repair cycles. And I'm plotting that G1C here in figure B, where you can see in comparison to our prior work in 2022, most recently, we've been able to achieve 1,000 heal cycles. Now, what you'll notice on this scale is we do see a slow progressive decline in recovery. And we were able to model that and fit that to a Weibull distribution, which is used to fit failure phenomena of this scenario. And that predicts that there is an asymptote, a non-zero asymptote, so healing will sustain predictably indefinitely. But we decided to take a conservative approach and say, all right, at which point do we have healing recoveries that match plain composite values, so we would never drop below allowables? And that's around cycle 500. And if we take that cycle 500 and look at different repair or healing maintenance schedules, either quarterly, semi-annually, or annually, we can quickly observe that recovery and asset lifetime extension is on the order of centuries, which far exceeds design life of these structures. And so we really believe that we have kind of suppressed and been able to eliminate this interlaminar delamination as a failure mode, That's not to say there are other mechanisms that may lead to failure in these structures, but delamination, from our perspective, is no longer a concern utilizing this technology. And we've got a manuscript coming out soon that will discuss all the operant mechanisms and things associated with this long-term recovery. And so with that, I'd like to conclude with a couple high-level ideas. We've been able to achieve in situ self-healing via the thermal remending and fiber composites below glass transition, which maintains structural performance. So this can be done in situ. The 3D printed EMA has negligible impact on structural integrity and increases mode 1 fracture resistance substantially. The textile resistive heaters, especially Gen 2, have minor impact on FRP properties. This tough EMA can increase that delamination resistance 2 to 4 times and enables high fracture recovery. And the rapid sub-hour extended healing cycles demonstrates a high propensity for practical and sustained in-service repair of DoD platforms. The benefits to the DoD are safer, more resilient composite structures, requiring less manual maintenance, repair, and overhaul, which equals lower downtime. The healing technology is a sustainable approach, environmentally conscious by reducing waste, and we can also reduce overall lifetime costs, which result in overall savings for any composite platform out there. And so I'd like to acknowledge the graduate students, 2 PhD students from the Multifunctional Composites group at NC State University, Alexander Steiner, who now works for a leading defense contractor, and Jack Turacek, who is looking at employment at a DoD laboratory, and also my 2 founding partners who helped form a startup company based on this technology and in part from the SERDP funding. And just like to acknowledge program manager John and also the SERDP program for providing the kickstart for this research. Here's some additional resources in case you're interested, publications describing some of the mechanisms and details that I didn't have time to go through today. And for additional information, please feel free to visit the website and contact me directly. I'd be happy to talk about this technology in detail and some further implements and additional areas that we're looking into. So with that, I'd like to thank you and happy to open the floor for any questions.
Wonderful. Thank you so much, Jason. And to our audience, just a reminder, please do submit your questions now using the Q&A box on the Zoom screen. And we have received a number of questions, Jason. First, what is the operating temperature range of this composite system?
Yeah, so the glass transition temperature of the composite is around 140 degrees C, so it's an aerospace grade system. And we've been able to show that if you can keep your operant range below about 130 degrees C or 120 degrees C, that this system maintains structural integrity.
Okay, great. And if we could now show slide 27. On slide 27, you showed that you showed the recovery rate after 1 healing cycle, but it looks like you also analyzed more cycles. And so what were the recovery rates after more cycles, like 10 or 20?
Yeah, so if you go to a later slide, I can give you that specific number where we show the 1,000 heal cycles. Let me pull that up real quick. Slide 32. Yeah, so you can see the healing efficiency. You can see the healing efficiency that evolves over 1,000 cycles. And so there is a progressive decline. And up to about 500 cycles, we're able to maintain fracture resistance well above the plain composite. And so, anything above below 500 cycles, you still have those recovery rates that are much higher than that 500 joules per meter squared of a plain composite. So hopefully that answers the question.
Yeah, I think that's very helpful. Thank you. What is the maximum crack size that can be repaired in this manner?
Yeah, so I think that really just depends on where you place the healing agent. And so we don't envision putting this material throughout an entire structure, but maybe in delamination prone areas that are identified by the end user. And so the crack size is really up to where the healing agent is dispersed. And anything that's within that zone can be healed. And through some of those pressurization mechanisms, the EMAA in the molten state is able to drive itself into, deep confined cracks and provide that recovery in any area that's been damaged.
Okay, thank you. All right, what about cost? Do you have an estimate of cost per unit weight of these composites versus the non-self-healing composites?
Yeah, so we're actually in the process of looking at not only cost in terms of an economic standpoint, but also an environmental standpoint, looking at a life cycle analysis. That's currently undergoing, but what I can say is that the EMAA is a readily available material adopted from food packaging industry. So it is fairly economical to incorporate into these systems. The resistive heaters are another element that incur some cost, but we are also looking at some non-contact methodologies for heating that don't require embedment in the structure. And so we expect the cost and the weight gains to really be minimal for these type platforms, very, very low, especially for the healing agent.
Okay, got it. Do you have any plans to examine more complex scanning patterns during the 3D printing?
Yeah, that's a great question, and we are most definitely doing that. That was one of the reasons for leveraging 3D printing, at least for some of these research studies, where we can print a variety of different patterns based on different expected crack propagations and type of events beyond just mode 1, but things like impact, etc. And we also foresee and are working on creating EMAA interlayers that are more scalable and can be integrated directly into composites and other processes, for instance, prepreg, et cetera. So there's a variety of things that we're looking at in terms of the distribution and integration of these EMAA interlayers.
Okay. Could this resistive heating technique be used to repair thermoplastic composites?
Yeah, great question. We've seen a lot of interest in thermoplastic composites. We are also aligned with that thinking. Yes, absolutely. It can be used for thermoplastics, and we also have some other heating technologies, wireless heating that we're developing that could also be used for thermoplastic composites. So yes, all the above.
Great. How do you know when to activate the thermal remending healing process?
Yeah, that's a perfect question. And at this stage, we know in the lab when the crack has been introduced into the sample. And so that's done by a manual approach. I actually just recently presented at a conference some new self-sensing technology that we've developed, and that publication is coming out soon, where we have embedded sensors that can not only tell us when the structure is fractured, but it can also tell us when there's crack closure, and differentiate crack closure from actually self-repair. And so we can self-repair that sensor. So we now have a fully automated, integrated self-healing and self-sensing platform that can provide that feedback, not only of damage, but also when the repair has been achieved. So that you'll see that coming out soon.
Very interesting. Do you envision that there could be entire structures, like an aircraft, comprised of self-healing materials?
Yeah, I surely think it's possible. I'm not sure that would be the most practical application, whether you would want to put this material everywhere or in kind of damage-prone regions. I think it would depend on what the criteria are. It's certainly scalable and certainly possible. I think what we envision is putting this in kind of hotspots or delamination-prone regions that could be closely monitored and repaired as frequently as needed.
All right, great. And Jason, just one last question for you. Would you please just summarize the next steps in this work?
Yeah, so I think next steps, we are working with a few DoD entities out there to identify platforms and not only specific platforms, but components and features where delamination is prone. And there are quite a few that we've had some very healthy discussions with. And so we're looking at how to then take this kind of lab technology and translate that into a commercial product. And again, looking at things like integrated sensing and healing to provide that feedback that the end user might need, but then also looking at alternative kind of heating, wireless heating strategies, and just make this as versatile and customizable as possible to the different composite platforms that are out there. So I think that's currently where we stand and where our mindset is.
Great. Jason, thank you so much for the presentation and for answering the questions. At this time, we will move to our second presentation. Our second presenter today is Dr. J. Brian Jordan, the Kenneth and Celia Carlisle Endowed Chair in Materials Science and professor in the Department of Mechanical Engineering at Baylor University's School of Engineering and Computer Science. There, he also serves as an associate director of the Point of Need Innovations Center. Dr. Jordan's research centers on advanced manufacturing and joining processes to develop materials with enhanced mechanical properties and tailored microstructures, with a particular focus on the relationship between microstructure and mechanical performance. His work has been supported by the Department of Defense, the Department of Energy, national laboratories, and industry partners. Dr. Jordan earned his doctoral degree in mechanical engineering from Mississippi State University. All right, Brian, please proceed.
Thank you, Jennifer. So thank you for the opportunity to present our research that's been supported by SERDP. And let me see if I have control of the slide here. There we go. So we're really our team that's been working on this project with the objective of developing technology and capability around repairing high-strength aluminum alloys in load-bearing structural applications. We're in the sort of in stages of the project, and so in this presentation, I plan to hit some of the highlights of some of the exciting work that we've been able to develop with our team. So in my presentation, I'm going to provide some background on aluminum alloys and some of the drawbacks of repairing those alloys, and then also talk about this solid state AM process that we're using to repair these unweldable high-strength aluminum alloys. In terms of results, again, hitting some highlights around some very specific particular repairs, including fastener holes that become damaged in galvanic corrosion situations. Also, some other types of repair applications, including a deep groove repair simulation. And then I'll couple that with some modeling and simulation results and then wrap up with a highlight of our corrosion characterization. And then I'll conclude my presentation with conclusions and then benefits to Department of Defense. So if you're familiar with aircraft, in particular assets of DoD, there's a number of structural components in either fighter aircraft or even cargo planes, for instance, that contain high-strength aluminum alloys, in particular 7000 series alloys. In this project, we've focused on 7050, and 7050 is a common high-strength aluminum alloy used in aircraft structures. These alloys have high strength, but they have well-documented weaknesses. In particular, they're susceptible to pitting, intergranular corrosion, and stress corrosion cracking. Complicating matters, these 7000 series alloys, most of them, and in particular 7050, are considered unweldable. And this is due to their alloying composition and chemistry. So because of that, some repair methods are needed and are currently being explored. So on this graph here, some examples that our collaborators have shared with us, highlighting the potential problem and the devastation of corrosion on these high strength aluminum alloys. And you can imagine Navy aircraft, for instance, they operate in very harsh environments. So corrosion is something that they need help addressing. When we talk about how to repair 7000 series aluminum alloys or high strength aluminum alloys, this list is just a very general list of methods that you might see in the aerospace industry. So when you've got cracks or that develop in the aluminum structure, or you've got loss of material, there's several approaches. You've got shot peening. So this can strengthen material around damaged areas, but it can't be used to replace loss of material or fill in voids. When you've got cracks, you can use techniques such as stop hole drilling. Again, this will retard crack growth, but again, you're not going to be able to replace a loss of material. Other approaches involve composite patching, but this has a drawback in that it can impact the flight dynamics. Filler materials or epoxies can be used to fill in voids or loss of material, but this introduces the potential for FOD, foreign object debris. When we talk about fastener holes, for instance, a common repair method is to use bushings to restore the geometry, but that has a limitation in how many times it can be used. So we talk about how to repair aluminum alloys. Additive manufacturing is something that is an obvious choice. And over the last decade or so, additive manufacturing has advanced very significantly. But when we consider common AM processes, intense thermal gradients are involved. So usually, if we for instance, highlight select laser melting, you're using a laser and you're melting powder together. So you've got, of course, intense thermal gradients. This, of course, and the way the process works for instance, in select laser melting, you've got a liquid to solid transformation that occurs in the metal. And this is necessary to get the powder to metallurgically join. It has some undesirable side effects, and one of those is you get the kind of microstructure that doesn't usually produce good properties. Those intense thermal gradients can also lead to vaporization of some of your alloying elements that are in your high strength aluminum alloy. And of course, in terms of fatigue performance, you can get hot cracking that occurs during the solidification. You also can get porosity. So that ultimately affects mechanical properties and reduces your fatigue strength. So there is a need for AM and repair technologies that input like on like material. And so what we're in this project, we've been exploring and developing the technology around using a solid state process. So we've been developing additive friction stir deposition for repair applications. And if you're familiar with friction stir welding is used, NASA uses it extensively in a lot of their large structures. It works really well for welding high strength aluminum alloys. It was developed several decades ago. So a derivative technology, this additive friction stir deposition, is very similar to friction stir welding. The main difference is it has a consumable part of the tool. So in a sense, you're consuming a rod that's pushed through the hollow tool, and this allows and accommodates the deposition that can be layer by layer. And of course, you can use this technology to fill in voids and other features that would be needed to repair particular geometry. So for our project, we propose to repair corrosion damage on structural components fabricated from these high-strength aluminum alloys, in particular 7050. So in close collaboration with our NavAir collaborators on this project, we selected certain problem areas and problem structures and features that are known to affect naval aircraft. And in this project, our two main objectives was develop the technical know-how to use additive friction stir deposition to repair and restore damaged areas due to, for instance, galvanic corrosion. And then also, in order to help mature the process, understand how this AFSD process modifies the microstructure and what sort of properties you get. So ultimately, we were looking at the relationship between process, structure, property relationships using this additive friction stir deposition technology. A little bit more background on additive friction stir deposition. What's unique about it is that this process allows us to do like-on-like material repairs. So the feedstock material is chemically identical to the substrate. So you've got this particular bracket, maybe a control surface hinge. It's got a very specific alloy, and so we can. The idea and what we're working on is making repairs where the filler material is identical. And so this additive friction stir process allows you to do that. Some other benefits, the depositions are generally, and the process is robust enough that achieving fully dense deposition is very reasonable and easy to do. We get microstructure that's refined and equiaxed, so we get wrought microstructure. And then we can control the process with temperature control feedback. So there's a lot of options and benefits of using this technology for repair. As a highlight overview of our presentation or of our project, we had four main tasks. The first task was really, again, developing the process know-how. How do we take this technology and deposit in very specific geometries, understanding that process window, the limitations, how much heat, how much deformation do we need? And then the interlinked tasks were understanding what sort of microstructure do we get? Can we simulate the microstructure and the deformation? And then quantifying the constitutive behavior. What sort of mechanical properties do we get? Static strength, fatigue strength, and corrosion behavior. Ultimately, again, with our close collaboration with the Navy, NavAir, we were concerned with making sure that we didn't make the damage worse. So if we're looking at repairing a component, we didn't make it worse. So we wanted to make sure that in the repair, we were providing a structural credit. So I focus on this first type of repair, this fastener hole repair. Again, this process is friction based, so the tool's rotating, generating frictional heat. The feed rods are pushed through that hollow tool. And in the case of a fastener hole, we're pushing the material through that hollow hole. So you can imagine you've got a fastener hole. It's got a steel fastener. You've got galvanic corrosion, so you've loss of material around that steel fastener. On the surface, if you pull the fastener out, you've also got damage along the shank of the hole. So as part of the process and what the Navy does, they'll machine away and they'll essentially oversize the hole. So our process starts with that simulated repair. So we've got an oversized hole. We push the extruded aluminum 7050 through that hole, and then we can machine it back to the original geometry. So this slide kind of shows you those steps. So that image at the top is sort of the progression. So we start with that oversized hole that was damaged due to galvanic corrosion. It's not the right geometry. It's supposed to be a 6.3 millimeter hole, so it's slightly oversized. The next step, we can put a blendette on the surface. So if we've got damage on the surface of the component and in the shank, so we've got that prepared, and then we do our AFSD process. So we're extruding material down into that fastener hole, achieving metallurgical bonding, and then we come back and do a finished machine and get it back to the exact geometries. And we followed NavAir guidelines on how to machine it and prepare the hole before doing any sort of characterization. That bottom image shows you some cross-sectional views of various variables that we looked at. So we looked at a range of things. So I don't have obviously enough space to kind of show you all of the variables that we looked at, but this is sort of a snapshot. This is showing and illustrating exploring the variability of dwell time. So this is the amount of time that we use before we extrude. So there's a little bit of a warm-up period, so to speak. And you can see sort of the progression of 10 seconds, 15 seconds, and 20 seconds and the effect of that material plasticizing and being pushed through the hole, whereas the bottom shows the material is fully dense. If you can see it, it may not be very clear on your screen, but there are some dotted red lines that represent the former geometry prior to the repair, just sort of highlighting where that original lines were. And so we're able to make with carefully controlled process conditions, we can make depositions that are defect-free. There's no visual indication of volumetric defects. We talk about performance, again, towards structural credit. The images on the left are, again, another cross-sectional view showing hardness. The depositions do reveal a very small, narrow heat-affected zone. And so the question was, does that affect fatigue performance? If we look at a finished repair, you can see that second image is showing, again, the dotted lines of the original blend out geometry before the repair, going from that oversized to that 1/4 inch. And then there's some EBSD images giving you representation microstructure that we do have wrought microstructure in that repair, and there's not any defects. On the right side is some fatigue testing results. So there's 4 groupings on the right side. Those are the repairs using AFSD. And we looked at and are showing 2 beneficial or promising results, rather, of the repair subjected to fatigue loading. So this data is on the vertical column, the number of cycles to failure, and then all these samples were tested at the same stress amplitude under a ratio of 0.1. And so you can see the dispersion of the data. The groupings on the left are the controls. So we've got the overside geometry and the blend out geometry. So these are the damage, simulated damage type fastener holes. Again, the blocks on the right are after repair. And so kind of the main distinction here, the one on the far right is where we actually took the tool and we warmed it up on a sacrificial substrate, got it up to a specific temperature, and then we moved over the hole and started depositing immediately. And we got significantly tighter dispersion of the data. Our average fatigue life is significantly higher than the control. The other process is where we dwell directly on the hole. We carried that out for a few seconds before pushing the material. We did show a structural credit, although the dispersion was significant. So, the takeaway from the processing is controlling that process by dwelling and getting to a very specific temperature, with monitoring the temperature with thermocouples before we go to component to repair it, gives us more consistent fatigue behavior, and it helps us to maintain more consistent microstructure. So that's the fastener hole highlights. So repairing fastener holes subjected to galvanic corrosion. The other type of repair we looked at was more substantial damage, deep grooves or loss of material. So to simulate that, to evaluate AFSD for repairing significant voids, we carried out a bunch of laboratory tests where we machined a relatively deep groove. So we're talking about a groove that's half the thickness of the plate. And we looked at several different plate thicknesses, to provide robustness to our repair. And then we looked at mechanical properties. So we're able to evaluate mechanical properties across that repair groove. You're looking at the as deposited image representative, and of course we machine that flat so that we've got constant uniform stress. This next figure shows you some mechanical property results. So stress strength at fracture for 3 sets of coupons. One's going to be the control, where we've got that groove and simulated damage, and then the one on the far left in the middle are the 2 repairs. Now the differences here is what we looked, and the variable that we looked at was heat input, and we can control heat input by varying the tool RPM and of course how fast we can translate. And we saw generally that we achieved higher strength, upwards to 25% increase on the ultimate strength of the repair compared to the control by limiting the heat input. So we, just for the sake of this presentation, we calling that a low heat input relative to our high input. The differences of these are, in the range of about, 50 to 75 degrees Celsius. But the other good takeaway here is that the repairs, both the low and the high, they failed in the repair. So what we were concerned about and we verified is that we weren't repairing doing the repair and pushing the failure mode into a different location. So this shows us that we can repair the damage. And if fracture occurs, it's going to happen in the repair. So it's in a repeatable sort of process, and we're not pushing damage to a new location. We also looked at the need for achieving returning a repaired part back to an OEM very specific yield strength requirement. If we just took a repair and performed a heat treatment, our yield strength wasn't sufficient. And so we looked at, from literature, we borrowed some concepts in friction stir surfacing where literature has demonstrated a second frictional surfacing that you can do over a repair. And this increases diffusional bonding. And so we incorporated that step in between the deposition and the heat treatment, and we were able to match the OEM yield strength. So this is a technique that can be used if you've got very specific performance requirements. Additionally, we developed simulation tools to predict microstructure, so grain size and intermetallic particles, the distribution and the size. In 7000 series alloys, iron-rich intermetallics can be the source, and mag silicon particles can be the source of fatigue cracks initiating in this aluminum alloy. So we used smooth particle hydrodynamics simulation tools to model the repair, incorporate its constitutive behavior to predict those microstructures, and then correlated it to experimental results. We also developed tools to predict, using the same SPH tools, to predict residual stresses in the repair, and we were able to calibrate and validate those predictions with neutron diffraction experiments conducted at Oak Ridge National Laboratory. And so again, these simulation tools are able to predict microstructure and residual stresses, which are needed in predicting fatigue behavior. And then lastly, in terms of highlights from our project, we compared AFSD repairs to baseline material using electrochemical testing and accelerated exposure. And the takeaway, the general takeaway is corrosion rates in the repair are faster than the control, but not substantially different. But we also want to acknowledge that our tests were done on bare metal. And so in a real application, if you take, for instance, a fighter aircraft, that's going to be performing operations on an aircraft carrier, that aircraft has a coating, and so our initial tests are obviously very aggressive because we don't have any sort of barrier coating on the repairs, and so we're currently evaluating and quantifying the corrosion rate with a barrier coating. So in conclusion, AFSD is a promising approach to dimensional restoration and provides a structural credit that can extend the service life of these unweldable high-strength aluminum alloys. We've demonstrated in the repairs of both fastener holes and some deep groove-type repairs that we can carefully control the process and provide a structural credit. We're not making the repair worse. and we can do these repairs with wrought-like microstructure, and there aren't volumetric defects present. AFSD can alleviate and homogenize the residual stresses. And our team has also, again, developed these simulation tools that can predict microstructure and residual stress that helps the structural engineers know what the sort of performance they're going to get out of these repairs. In terms of benefit to the DoD, AFSD, again, has a huge benefit in that it can repair one-to-one material. So it's like-on-like repair. These repairs can be done, locally, on-site at depots. And of course, the technology has the capability to do other types of repairs and depositions, so dissimilar and high-performance alloys. I didn't actually talk about this technology, the other uses. You can use this to actually build near net shape components. So if you have a component that the OEM isn't in business anymore, and that part or the company doesn't want to turn on the forging machines again and retool to make a very specific part, this technology can actually do layer by layer deposition. Obviously, in the repair, it's like a one pass, one layer type approach, but you can do layer by layer build up. This technology has really fast deposition rates. In our lab, we've demonstrated that we can lay down 60, 70 pounds an hour. So to build relatively large parts, casting and forging replacement type parts, the deposition rates are such that you can do that. And we've demonstrated also this technology is cost effective. This technology is an open atmosphere, so there aren't expensive gases or environments that you have to maintain. And the feedstock is the same material that the part is made out of. So there's not any special chemistry or processing that needs to be done to make the deposition. So I do want to end real quick by acknowledging the great team that's been working on this project. So Paul Allison, Pedro Reyes, and Ning Zhu at Baylor, Luke Brewer, Greg Kubecki, and Matt Kasemer at the University of Alabama, Kevin Doherty at Army Research Lab, Chris Hess and Alan Timmons at NavAir, and all of the great students that have worked on this project. Some have graduated and gone on to the next step of their career, and then of course the current students work on the project. So really thankful, a great team, made a lot of good progress. Please reach out to me. There's my email. You can call me as well. Please check out our project for some more information, and I'm happy to take some questions.
Great. Thank you, Brian, very much. A reminder to our audience, please submit questions by typing them into the Q&A box on the Zoom screen. First, if we could please go to slide 50. The question there was whether the samples were fatigue tested with the fastener hole geometry, and if so, and if you include the stress concentration factor, was the maximum force above the yield strength of the material and the repair?
Yeah, so if I think I understand the question, was the maximum applied stress above the yield? So this is a great question. No, it wasn't. So this was the stress was below the yield on these samples. But I'm also happy to talk in more detail about this offline.
Okay, great. Thank you. Next, how portable are the AFSD machines to get into close quarter compartments?
Yeah, such a great question. A lot of the development of this, technology for this project happened in our lab, and so we've got, a lab machine. There's a lot of conversations about this technology. The nature of the technology is that it's scalable, so we can scale up and you could scale down. Obviously, there's limitations kind of both ways. We and Baylor and Alabama and some other folks have been in a lot of conversations as to what does this look like to scale down. We have also actually developed, scaled down this technology, and we've demonstrated that we can repair and make depositions on smaller features. So definitely the size is a constraint and a barrier, but there's a lot of efforts that us and other folks in the field are addressing to scale down this technology to make it as useful as possible. There may be certain types of repairs that still require you to take the part off. But I think, part of what we're looking at, sort of the next steps of this project is, we did a lot of this on coupon level development. The next step of this project is, the next steps would be to, do repairs on actual components. So, the idea here is to take this the geometry of a representative component and make depositions on a real life component and evaluate the structural credit for those components.
Okay, thank you. This next question is from the Air Force Sustainment Center. How easy or time consuming is it to switch materials? The limited space or costs could prevent having dedicated machines for each material.
Yeah, this is a really, really insightful question. So, from a repair point of view, you can operate this with very short filler rods. So you can operate this really in a discrete manner. So the technology is such that, of course, you can do additive manufacturing and have a build that runs 48 hours that makes some really large part. But obviously, when it comes to repairing, the technology, and you can operate the machine in such a way that you can feed it one distinct rod. Unlike other AM processes, and I think maybe this is where the motivation for this question is coming from, right? Switching materials, because you're talking about powder. If you got a powder bed, right, you have all this extra material, and it tends to contaminate, and you can't switch easily from steel to aluminum. In this this additive friction stir process, it's a completely different situation. And because the rod is just being extruded through, the throat of the tool, there isn't any sort of contamination. When the rods, you can replace that consumable rod with a different material. When it comes to specific alloys, if you're talking about depositing aluminum versus maybe titanium, you do need specific tooling. The rule of thumb is that your tooling needs to be harder than your feed rod. So tooling for aluminum repairs is going to be like tool steel. But then if you're depositing steel, you need something harder than that. So some tungsten, advanced and special alloying tools, that allow it to deposit, hard things like steel or titanium.
Okay, got it. Thank you. This next question is from Naver, and it's a little detailed. So let's see if you'll be able to follow it. For R equals 0.1 loading, the maximum stress in the hole is above the proportional limit for low cycle fatigue. Can you describe why you think the post-cladding operation returned the 7050 to peak strength?
So I think he's talking about this next slide here. So maybe go to maybe the next slide, 52, 53 maybe. Yeah, so what we found when we did a heat treatment on the fastener holes, or on this deep groove, the yields, the heat treatment tends to create some issues with the strength of the diffusional bonding, the metallurgical bonding. And we found that using this intermediate step of hybrid frictional diffusional bonding step. So we make a deposition repair, and then we come back with a second step where we run essentially a flat friction tool over the repair. And this just is inducing some additional thermomechanical processing. And what we found was this increased, provided additional strength to the metallurgical bond. So it promotes additional diffusion across the repair interface. And then when we carried out the heat treatment, that interface was sufficiently strong enough that under the applied strength, the repair didn't fail. So I think that's answering the question. But again, I'm also happy to NavAir folks, I'm happy to send you the manuscript or have an offline conversation, more detail about that. But that's kind of my understanding, kind of my take on why the diffusional bonding increases the strength of the repair after a heat treatment.
Okay, great. Thank you. Can you talk about qualifying the process? Has your team and NavAir started working on that?
Yeah, so that's a really great question. If you talk to and some of my NavAir colleagues are here on the call, I think, there's several steps that are involved to qualify a repair to make it airworthy. I think and that means identifying the part and identifying the requirements and a lot of testing, verifying, making sure statistically, you're getting consistent repairs, consistent performance. I think the step before that is the demonstration step. So we need to repair a realistic part, so maybe a part on an F-18 that's prone to galvanic corrosion, maybe a fastener hole. Do the repair. I think that involves, developing tooling for that. It may require specific tooling to get around very specific features of that part. And then perform some mechanical evaluation to verify that we're still able to provide a structural credit. And then I think once that step is done, I think that's kind of the precursor to qualifying this part for airworthiness or the repair for airworthiness applications.
Okay, great. We have just a couple more questions. What is a typical RPM that the depositing head rotates at?
Yeah, great question. So, there's several different manufacturers that have technology for additive friction stir deposition. That range can be, a couple hundred RPMs to several thousand RPMs. So the process varies, but there's sort of a range of RPMs that various manufacturers can do. A lot of the range of the RPMs is kind of similar to, what you'd see in machine milling operations or friction stir welding. So a couple hundred to a couple thousand.
Okay. And finally, is any surface cleanup needed before the repairing?
Yeah, such a great question. We actually looked at this. So obviously the results I showed are kind of, are like laboratory type setting where we've machined it, we Scotch Brite it, so the surface is clean. It's clean of oils, contamination, and we showed that we can repair, that geometry and achieve a structural credit. So the question is, well, you have a pristine prepared surface. What happens if you have a corroded fastener hole? You take the fastener out, you have some exfoliation. You've got pitting, you haven't machined that away. Can you deposit directly on it? And the answer is yes, you certainly can. The mechanical action, the stirring action, will deposit the material and stir that up, and you do get metallurgical bonding. The unknown part is, do we get a structural credit? And that work is still ongoing. So we're in the we've repaired. So we've actually sent our colleagues at Alabama who are evaluating the corrosion performance. They've corroded samples and they've sent it to us, and we have repaired them. So we know that we can get the material to metallurgically bond to that as corroded surface. And we're in the process of testing those coupons to see what sort of, if there is any knockdown on performance. So it's a great, insightful question. We hope to have an answer on that shortly.
Okay, wonderful. At this time, we're going to wrap up our webinar. Thanks to both of our speakers today for the very clear and informative presentations and answering the questions. To our audience, please remember to visit the SERDP and ESTCP webinar webpage to register for the upcoming webinars. And before we conclude, I just want to remind you both the audio and a copy of the slides from today's session will be archived on the webinar webpage in case you want to refer to them in the future. We would appreciate it if you could please just take a moment to complete the survey that will pop up on your screen at this time. And this concludes today's webinar. Thank you all.